As he shares his presentation, Planet has been a strong supporter of the Precision Ag Conference, so I really want to thank Planet for their continued support of this conference, because we think it's very important that we continue to share the technology that's going on in agriculture. When Planet first started supporting us, they didn't even have a Dove, and now they're small satellites, and now they have a whole bunch of new ones coming up, over 200. So it's pretty amazing how far they've gone, and their new technology, which Cassidy is going to tell us a little bit more about, is going to be pretty exciting as well. So please welcome Cassidy.
Well, good morning, everybody. I'm glad I didn't have to go first this morning. Thanks, Josh, for talking before me and grounding us, getting into the soils and really the stuff that matters to plants. We're going to go a completely different direction, and we're going to go way, way up in the sky, even above the sky, into space, and talk about satellites and Planet Labs technology and where we've come from. And really, this talk is going to be about what's new with Planet. So for those of you maybe who don't know what Planet is or does, could I get a show of hands if you've never heard of Planet? Okay, so there's a few. That's helpful. All right, so some of you have heard of us, and maybe some of you have worked with our imagery. So I'm going to talk about what's really new and coming down the pipe, but to start with a bit of a refresher maybe, we'll go over the basics of what Planet Labs has built, and really what Agile Aerospace means and what it means for agriculture and precision agriculture. I don't know if anyone here has ever tried to contract somebody to build software for them or has played around in software development, but if you have, you'd be familiar with the concept of agile development. And the way I like to describe trying to hire someone to build software for you is kind of like picturing something in your head that you want to have built by Lego, and then describing it to someone else and have them build it for you. And you can imagine that it doesn't always come out exactly how you want it or expect it's going to turn out. And so we can't use the typical kind of way of building things like we do, like a house, for example, like a blueprint that you follow, and then it pretty much should turn out like that blueprint. With software, there's always quirks and different visions and challenges. So agile development really came from software development, with the whole concept of let's plan it out, let's try to execute on it, and then let's check back regularly with what you've built and make sure that it's working as we kind of hoped it would, and then test it out, iterate on it. So that's really the whole concept of develop quickly, make sure it's working as we want it, find the faults, improve it, make it better. And that, a lot of us do that in farming. That's a common thing, year over year, learning from mistakes. That's not something that's been possible in the aerospace industry because it's very expensive to build this technology. It's very risky to put it up into space. And then you have all the challenges of operating something remotely that you can't ever really touch again and fix. So Planet really pioneered this idea of Agile Aerospace, of building things that we could iterate on quickly and improve. And there's lots of advantages in building space technology that way for applications in agriculture and agriculture digital technologies. Hey, it's working. So remote sensing or imagery is not new in agriculture. Many of you have seen or worked with imagery before. Maybe some of you are experts in imagery interpretation for precision agriculture management. That's fantastic. I've come out of the University of Alberta's Center for Earth Observation Systems. I did my doctorate in understanding how accurate satellite measurements are for plant growth and plant physiology and doing ground validation. After that, I started a drone company and tried to use drones to map out fields for precision agriculture. Really, really fantastic technology. It kind of democratizes our ability to collect our own imagery, which has never before been possible. But you'd be familiar with the challenge of trying to use a single image in time. You get a snapshot of your field at one point in time, but we know that field is changing and evolving all the time as the plants grow and weather changes and new risks come into play. So in agriculture, the challenge has always been limited, coverage. Where can I get imagery? Do I have to go fly a drone? Do I have to get a plane? Low revisit rates, so we might get 1 or 2 or 3, if you're lucky, more than 4 images in a growing season. And then it's really difficult to get at that data. So if anybody's ever wanted an image of their field, maybe you've hired somebody with a drone, maybe you have your own, maybe you've got a neighbor with a plane that can go out and take photos. It's not necessarily easy to get that imagery into a workflow that works for you. Your agronomists or some of the digital technology providers have probably filled some of those needs for you, but to do it yourself is really difficult. So to kind of create an analogy of what it's like looking at an image of your field and finding problems in it, I'd like to put your attention to this picture. So we come into a room in our house, we've been away for the day, we find our room in a state of disarray, there's problems, and we immediately we look and we say, okay, I think I know what this is. I have a lot of dogs. This looks like a dog, this smells like a dog. It's very likely a dog that did this, right? But maybe you don't have just one dog, maybe you have lots of dogs. And maybe there's 1 or 2 or 3 troublemakers in that group, and you don't know who did this, right? So you kind of have to guess. Maybe you have to punish more than one, or maybe you have to punish all of them and try to train that out of them. So there's a lot of guesswork in there. You're pretty sure what the problem is. Let's treat or over-treat for a few things. There's a lot of uncertainty. So for those of you that have looked at an image of a plant health map from satellite or from drone, looks something like this, a red-green map. Red is bad, green is good, yellow is in between. And you can generally pick out patterns that make sense, right? Maybe there's cedar misses, maybe there's a wet area we know doesn't grow every year. If it's your field, you're pretty familiar with areas that aren't working. If it's a field you've recently just acquired or started working on, or you've never seen it before, now you've got to do some guesswork in some of these areas that are red and what might have caused those problems. And that's really been the state of imagery in precision ag technology. You can make pretty good educated guesses on what's causing those issues, but you don't always get it right. Planet has the philosophy that you cannot fix what you cannot see. And it comes from the old adage, you can't manage what you can't measure. But when we're talking about problems, we know we want to fix them. It's more than just managing. We need to see what's happened and how to get there to that solution. So Planet's mission, which started just over 10 years ago out of a small startup in San Francisco, was to image the entire planet's surface every day. And that's a pretty ambitious goal for a small group of people trying to compete with some of the big aerospace technology providers in the world. And the whole idea is that the more you can see, the more accessible that information becomes, the more actionable the solutions to those problems become. So that's what Planet did. They put enough satellites up in space using this Agile Aerospace, build quick, deploy quickly, fix problems fast, to get enough satellites out there to monitor the entire land surface every day. And what you can then do is start to see patterns and trends over time and create insights on how to manage those issues. So a quick look at our constellation. The Rapid Eye is a bit of a legacy one that was acquired when Planet bought Blackbridge in Lethbridge, Alberta. So deep Alberta roots. Our flagship constellation is our Planetscope. So just over 180 doves. What we call our Planetscope constellation is our always on, always monitoring. And then we've got high-res tasking satellites, so 21 of those that go around and kind of a point and shoot where you want it to get a nice high-res image. And that completes most of the constellation sensors. And this is a look at what that actually looks like. It's basically a line scanner around the Earth. So as the Earth rotates, we've got our Planetscope constellation going in a north-south orbit and line scanning as it goes. And then to complement that, you can see the blue lines there is our SkySats. Those collect 50 centimeter imagery, and they're tasked to different locations to get a closer look at things. So this is the largest ever constellation of Earth imaging satellites ever built. And really, I mean, a lot of the land area being agriculture, that was a big market that was ready to be kind of disrupted in terms of access to imagery in places that you normally wouldn't have it. So I'm going to blast through a lot of information here today. Going to cover a lot of things and move pretty quickly. So if you have questions about any of this, we're here in the booth and here for the rest of the day, so be happy to chat with anybody more about this. But lots changing, lots kind of evolving all the time as we learn from what we've built and the data coming out of it. So we think we've solved the challenges of remote sensing in agriculture and a lot of other applications, where we've now got high frequency, 24-hour revisit for every acre of land area on the planet. So we've got complete coverage. It's no longer, do you have imagery here for this specific date? We have imagery everywhere, every day since 2016. We've got API access, so if you're building a automated workflow off of our data, you can set that up, pull in the imagery as you need it, clip it down to an individual field or an individual hectare, make it really ingestible. And so to take a look at the difference between what used to be available versus what's available through Planet's imagery now, this calendar view kind of gives you a typical look of imagery coverage from public satellites. So many of you maybe know of Landsat or Sentinel-2. And you might get a couple collections in a given month, but not nearly enough information to kind of track plant growth effectively at key growth stages. And I would kind of compare this to using maybe a public Wi-Fi to run a business. You could go to the library and you can get free internet, but you're not going to build a business there. You're going to want to get a dedicated line. You're going to get high frequency, reliable information streams. So you can do R&D and you can kind of test the waters with publicly available imagery. It's lower resolution, much lower frequency. But when you want to really scale your business and operate effectively and efficiently, our imagery really solves that problem. So we get a lot more chances of getting cloud-free imagery. So the clouds are a problem. They're always going to be a problem in optical remote sensing. And what that looks like if you're only looking at a plant health map or an NDVI, if you're not looking at the optical imagery and you're just looking at an NDVI, clouds are problematic. And if you're building algorithms that are change detection on it, and you're not necessarily picking up like a cloud flag, for instance, you'll get the wrong idea of what's happening in your field. So clouds are bad. We don't want them. In terms of scaling, this is just a look at about 1 million hectares of growing area. If you were to try to capture that with a drone, you would need a heck of a lot of drones, over 100 drones running all day just to collect that imagery for a single day. So not a scalable solution, though I love drones. I fly them all the time. This is an example of resolution comparison from Landsat to Planetscope. So pretty big difference in what you can actually pick out with the human eye, and then a lot more information can be picked out with a computer. So spatial resolution matters. Those of us that have been spoiled by drone imagery are familiar with the ability to really zoom in on like almost individual plant level. That's not the scale of imagery we're getting, but if you're using a low-cost imagery source and trying to use satellite for continuous observation, you can compare what you'd get from like a Sentinel image to what our Planetscope gets at 3 meters, and then if you were to zoom in even closer on our SkySat scenes at 50 centimeters, you'd see a lot more detail. So what's really new about this is that we've got a deep archive of imagery now. We've got imagery collected for years and years, over and over now. And so we've got this rich learning library. If you're trying to build an algorithm on this data set, we've got over 2,000 images for any location on the Earth's surface and growing every day. And so you can train machine learning models on that and deploy them to work on our real-time imagery. And really what that gives you is like a time machine, the ability to look back at any day you want as well. So if you've got a problem you're trying to find in a field from years back, having this time machine capability is something we've never had before, where you can usually get an image within 1, 2, or 3 days of when you're trying to find something. So going back to the way imagery has traditionally been used for agriculture, if you're literally just visually using that imagery to do interpretation and scouting, a little hard to see this image there, but there's a dead patch. It's a color infrared image, so the infrared band. The less red, the less healthy the plants. So you try to have to work backwards and really fill in the gaps in what happened. But when you can get a scene going back days and weeks on end, you can actually see how those problems have evolved over time. So you've got not just an idea of where the problem is, but also where it came from. And you can really narrow down what's been driving that loss. So you can do this visually now, but you can also train machines and computer models to be able to do that for you and do it with much greater accuracy than if you're just trying to take maybe ground data and correlate it to one single image, because you've got this pattern over time. And really what that means is less time ground truthing. less time working with electronics in the field. I don't know about you guys, but trying to use a laptop or a tablet or a phone in the field to find spots on the map and find them in the field. I very much dislike trying to use a screen outdoors when it's bright out, and you'd be hard-pressed to find a screen that doesn't glare. So if you can get to that solution with less ground data for problem solving, the better. So coming back to this scene, imagine you had a motion camera in place for this scene. You can now go back and see, who done it, who's the guilty party, and maybe it wasn't your dogs at all. Maybe it was John, and John was just trying to get a new lazy boy, and he made a mess and blamed it on the dogs. So what's next? So this Agile Aerospace approach. So we've been operating for a few years now and providing imagery to a lot of ag technology companies, a lot of people doing research, a lot of people building new things with imagery that's a new way of seeing fields change over time. And we get all that feedback, and we learn and we iterate. And so we've launched several new, what we call flocks of doves, into the constellation over the last few years. The most recent generation is called our Super Dove. It's now got 8 spectral bands of information, adding to the previous 4. And so I'll go through those examples and show you guys what's really new and exciting in that world. So with over 200 satellites in orbit now, many generations of the sensors have been improved, the capabilities of that technology, the way we deliver and aggregate that information and make it accessible to people has all been improving. And the latest and greatest information is basically more spectral resolution, meaning you can do more analytics, you can train more machine learning models, you can find more things and do more than you ever could before without that type of spectral resolution. So we've built 14 rounds of these doves, and we launch them a couple times a year on average. They go up on SpaceX most of the time. And they've got a pretty quick development cycle, just a couple months. So once or twice a year, we can get a new batch and improve on what we've got. And then we're not at risk as well as failures. So if anyone's used Sentinel imagery, you might know there's 1 or 2 satellites out there. And when they go down, you're kind of out of luck because there's no quick, easy way to replace that information. So the idea of if we have some sort of failure in there, we can quickly get things up and running. There's redundancy. It's just a new way of doing aerospace. So this is what the spectral bands look like now. Kind of comparing Sentinel-2 is what a lot of people build solutions on at the top there, so wavelengths of light that we're collecting. Our old generation, the Dove Classic, used to be broadband, really a lot of overlap between that, which makes it hard to do a lot of plant health analytics and detect different types of disease problems with as much confidence. Now with the Super Doves, we've got more narrow wavelengths of light. We can actually determine different types of diseases with more accuracy. And then we've added in a red edge band, which you can see we're starting to align with the scientific mission called the Sentinel-2 satellite. So they become interoperable effectively. Now you won't be able to read this. Come find us and talk more about what those new spectral bands are and why we picked them. We've got additional yellow and green bands in there. You can start to do some really cool plant physiology and understand light use efficiency, water use efficiency, if you're trying to do research on biomass and carbon. And this is a fantastic tool to now facilitate all sorts of different environmental, social governance metrics, monitoring, reporting, validation, verification of things, product trials over time, understanding how they're reproducibly measuring how crops are performing. And being able to do that anywhere on the Earth's surface anytime is a massive advantage. So if anyone's used Planetscope imagery before, it might have looked a little blurry in the past. We've been called spectrally challenged, and part of that comes from the fact that we're packing a whole lot into a very tiny form factor, right? So it's not $100 or $200 million satellite, it's a $100,000 satellite. And so what we've been able to do with each generation is improve the clarity, the sharpness, calibrating that signal so it's harmonized with the scientific grade measurements. And we've rolled out it's a big combination of all those improvements this past spring. So there used to be these hot pixels that you'd find often in the imagery where the sensors get saturated from too much light. We've corrected that. Those are called hot pixel corrections. So we've pulled that out of the pipeline, and it may look like a minor difference, but it can make a big difference in an analysis. The sharpness and clarity, we've done a whole bunch of work to kind of improve the band alignment. These satellites are moving at thousands of kilometers an hour, so each one of those light bands are collected as you're moving. And so there can be a little bit of blur and cross-contamination, and you get kind of a blurry-looking image. So we've done a lot of work to correct that. If you do go back and look, if you do have a Planet subscription or access to our imagery, if you look at last year's imagery versus this year's imagery, you'll notice quite a big improvement in the clarity of those base maps, where we actually create a cloud-free mosaic every 30 days for the entire planet. We could do that every week or 2 weeks for a given area as well. And this is kind of what that improvement looks like, which you won't be able to tell from this slide, but when you kind of start to zoom in on edges, you're getting blur and you're getting spectral band alignment. So that's it may look like a minor difference, but we've got millions of photos taken every day, so it's quite the process to improve. And we've taken feedback from all of our users and put it into this. And then what is really exciting for me as someone who's like a remote sensing nerd is we've taken that signal, which can be noisy between all the different sensors, because we've got all the satellites passing over. We try to be around solar noon every day, but it's a different camera sometimes on different days. And so those gray dots there you'll see over time as an NDVI index going up and down throughout the season can be a little bit noisy, and it can be hard to pull out what's actually happening and what's noise and what's actually signals coming from the plant. So we've radiometrically harmonized that to the Sentinel constellation, and we do some more advanced calibration of that signal. And to go one step further, we've built a product now called Planetscope Fusion, which merges all of the imagery from all of the different satellites out there, not just ours, but also the big scientific grade missions from NASA and European Space Agency. And we've created a beautiful model called Planetscope Fusion of a daily cloud-free, perfectly radiometrically correct image, meaning you can take measurements day over day and compare them between site and between days very accurately. And we gap fill everything, and we create this, what I would call a God mode of remote sensing data, because you can track plant phenology very accurately. You're not dealing with signal to noise anymore. And you can do some really cool science with this and some really cool R&D. You can measure carbon sequestration, you can measure overall productivity. We've got lots of people doing research on soil science with using these signals because they're no longer contaminated by atmospheric information. And just to show you what that looks like, here's a video that will be comparing kind of our daily scenes on the right. So you get all the clouds, you get all the imagery that gets messed up by the atmosphere and kind of scene boundaries that cross with each other. So if you flip through our daily catalog, it'll look something like what's on the right. So you get a cloud-free scene about once a week, maybe twice a week in most places. In drier spells, you'll get daily cloud-free. But with our Fusion product on the left there, you're basically like a video camera sitting over top of the landscape, getting really clean imagery so you can pull really meaningful information out of that. You can see pivots get irrigated. You can start to see different machines in the field, plowing or combining. It's a whole new world of information coming from these satellites. And then we tried to make it really less complicated to understand our data sets from the back end, because we've got all of these different satellites and they're different generations and they've all got different names. And so we really consolidated the way that you would interact and understand how to programmatically access our information. So all that's been consolidated. We've added 8 spectral bands to anybody that has an existing subscription. That's the beauty of Agile Aerospace. We're not charging you more. We're just making it better continuously. And so what we can start to do is some things that have never been really done before with satellite imagery in agriculture. So there's lots of new use cases coming up. This is really the traditional way people are using imagery and satellite imagery, right? The most common one you'd be familiar with is zone management, creating these management zones from imagery. Directed scouting is the other one. You get a nice plant health map and you go figure out what's causing those problems. Now that we've got this red edge band, this is a plant reflectance signal in different wavelengths of light across the bottom. So the visible bands there on the left, and then you start to get into some infrared bands where you see a lot higher signal coming off of healthy plants. What happens when plants start to get stressed, right before that line starts to climb up, it's called the red edge, where the light really starts to reflect like a mirror off of plants. We get really strong shifts in that when plants start to stress before you can see it or before you can pick it up with like an NDVI map, and that's called the red edge band. So we've added that to our new sensors, and it really improves the ability to create meaningful visual maps of plant health after you've got full canopy development. Once your field fills in and you've got multiple levels of leaf area, most indices like NDVI will just saturate out. You're not seeing any in-field variability anymore. So that comparison of the two figures on the bottom left there shows you what the red edge band can pick out same time, just taking a different wavelength of light. This is another look at that same thing where we're comparing the most commonly used plant health index, NDVI on the left, where we're kind of July, fully closed canopy. We're not seeing a lot of in-field variability, just that signal is really saturated by too much plant biomass. And then the chlorophyll red edge index for the same field, same day on the right. And then looking at an aerial image of some spots that are clearly showing up clear as day in that red edge index, but not in the traditional NDVI map. So we've added all these extra spectral bands through our APIs, so you can bring it into your workflows if you've got imagery in your workflows. We've made it as easy as possible. You can calculate those indices on the fly, so you don't have to pull down imagery itself, which is quite heavy, and you may not want the actual imagery. You just want some lighter weight spectral indices. With our calculators on the back end there, you can just say, I want to pull an NDVI for this area of my field, and it's a lot lighter weight information that way. So how are we doing here? We got a little bit of time left. Perfect. I think I got 20 minutes, right? So what's next? So we're following the same Agile Aerospace philosophy, and we're building next generation things. The first one I'll bring up is our Tanager mission, which is a hyperspectral system. So we've been building this with JPL and Arizona State University, and it's going to be a bit of a different beast. We're not going to have hundreds of them out there. We're going to start with one or two, and they're going to start going up next year. But it's a hyperspectral camera. And so there's a few other space companies out there doing hyperspectral. We've done our homework, and we feel that this one is kind of the Cadillac of a hyperspectral system to put in space. It'll have over 400 spectral bands, so you can see what our current sensors are measuring in terms of the wavelengths of light on the left. And then when you look at the Tanager system, many, 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 many more wavelengths of light, so you can start to do some really advanced remote sensing calculations. And that's a lot of data, and that's a lot of stuff you probably won't want to crunch yourself, but I'll get to some solutions there in a second. The other one I'll announce is our very high resolution constellation that we're building. This one will also start going up next year. It's called the Pelican. It'll be closer to aerial imagery quality, which is around 30 centimeter imagery, potentially more than just 4 spectral bands as well. All the details are not fully released yet. This is just kind of an early look, but we're going to put a lot of them out there. So right now we've got our always-on constellation that's doing a 3-meter pixel updated every day. We've also got our high-res 50 centimeter tasking. There's 21 of those satellites, so it's the largest sub-meter imagery constellation out there. Pelican will have even more of those and higher resolution, so we're looking at putting 30 to 35 of those up into orbit, and that means that you can get imagery within 30 minutes of requesting it. And then the thing I'm probably the most excited about that we do have now today is called our planetary variables. And this goes a little bit outside of what Planet has normally offered in terms of imagery. It's actually microwave satellites. So it's passive microwave information, so it sees through all the clouds. We're not interfered by the atmosphere at all. And we're measuring water, vegetation, and temperature. So soil water content, vegetation biomass, and land surface temperature. So these are key plant growth variables. We measure that on a daily basis across the globe. Somewhat lower resolution than you would see from an optical satellite image, but what that looks like is 100-meter pixel, but updated every day. So it's like having a soil moisture probe every hectare on the landscape, but completely remotely measured. 25 years of scientific development to get to the point where we can reliably say it's within a few % of actual ground measurements. I've seen some very exciting data coming out of the science team that has developed this product. They're world experts in microwave remote sensing. They basically wrote the textbooks on how to do this. So really cool product, and being used by some insurance companies around the world now for basically countrywide drought insurance programs. So if they put their faith in it, then I do too. We've got land surface temperature coming down the pipeline yet. There's some early access availability, but it's not fully available. And then a biomass data set. So this is actually a 10-meter resolution pixel, daily biomass to actually track plant growth without any of the saturation effects. Again, these products aren't really intended to be used for your eyes to look at, and interpret. They're really designed to put into workflows and use in algorithms. So what that kind of looks like, that constellation, it's a virtual constellation of different satellites that have been built by different groups. And where the proprietary bit comes in that Planet developed with a company called Vandersat is the ability to take that signal, clean it up, really make it very, very accurate and much higher resolution, about 100 times spatial resolution higher than what you would get from those satellites otherwise. So there's a lot of science that goes into this. I'm not going to go too deep into it. I'd love to chat with anyone more about the technology and the science behind this. But safe to say that having a continuous time series of these over your fields and over different areas is a very powerful tool. Let's say you want to claim that you've been improving your farm practices in one way or the other, and you want to be able to validate that. You don't necessarily want to build a sensor network yourself or hire somebody to do that, which can be very expensive and time-consuming to do. So having these data feeds come from space in a reliable, standardized way that works across space and time can really improve measurement, reporting, and verification. So this is the product we have that you can actually buy today, soil moisture monitoring for your fields. Again, I could give a whole talk on this stuff, so I'm just going to leave it there. Come talk to us more if you want to learn more about it. Here's some validation of time series of probes on the ground. We found to get an accurate representative measurement on the ground, you need maybe 20 sensors per acre to get a spatially representative measurement from a probe, compared to these signals, which are broad area, right, over a given 100 meter by 100 meter patch of land. So you get a lot of very hyper-local variation, different soil densities and different compaction and different air pockets that can all affect that measurement when you're using a probe on the ground. So it is very difficult to do like a one-to-one comparison. But we do know that when we measure the yield and we measure the plant productivity, this soil water data coming from our satellite sensors is very reliable and very, very, very accurate. So when you bring these all together, land surface temperature, soil moisture, plant biomass, some of the optical spectral information where we're looking at disease pressures outside of just the meteorological conditions, we can create some very powerful yield models and some really cool, hyper-local or very regional, even continental scale tracking and predictions of yield forecasts, for example. So we're predicting better than the USDA forecast on average, 12 days out, about 25% more accurate. And we've got a lot of clients that are using that intelligence for commodities and trading. And it's a bit of a game changer being able to do this any given place you'd like. Now that's complicated stuff, and we could go really deep into that, and I don't want to do this on this talk. But that brings me to my final section, which is what Planet is offering as a professional services group. So this is relatively new at Planet. It's just evolved over the last 2 years. It's called our ProServe team, and really they're there to accelerate solutions. So you're not a remote sensing scientist. You're not a precision ag expert. You're not somebody that is wanting to dive really deep into the weeds or hire a full development team to build something on our data. Our professional services team can do that. So it's really about accelerating time to solutions. So you've got an idea, you want to use our imagery in some way, or our data for one of your SaaS solutions, or maybe a new agronomic research project you've got. We've got the scientists, we've got the integrations, we've got the development experts, and we want to make sure that if you want to have a low-risk way of trying to work with this data for the first time, you could do that with us. So we're integrating with existing workflows, existing softwares, try to make the process so that it's not a high-risk thing to do. And so we've got a lot of experts on that team that can help with that. So we actually do pilot pilot project workshop program. So you come to us with an idea or something you want to implement, or something you've seen someone else do but you want to do it better. We'll brainstorm it, we'll de-risk it, we'll scope it out with you, and then we'll build that prototype with you, and then away you go. You keep the IP, it's yours. So really accelerating that time to value. So we've been doing this for the last year and a half with a lot of clients with a lot of success. They found that they've cut down their overall cost to try to implement a new remote sensing or imagery workflow by a factor of about 10. And I don't know if you've ever tried to hire developers, but they're not cheap. And so this is something that we're pretty happy to offer. So looking at the full stack of what Planet's offering and where we're at today, we've got the foundations. That's the hardware, that's the sensors in space collecting imagery, collecting data all the time. Interoperable with other satellite data sources like Sentinel, Landsat. We've got archives, which is very unique, that we've got imagery that goes back many years. Looking at our rapid eye constellation, we get imagery back to 2009. It's almost a 10-year solid time series of pretty high frequency imagery. Then we've got all of the tools to work with that information in an efficient way. You don't have to buy a whole scene at once, like a scene is a couple hundred square kilometers. You can just give a little polygon for your field or your research plots and subscribe to the pixels just coming out of that one little area and just pay for those pixels. It's a much more efficient way of interacting with this big data. And then, as I mentioned, we've got our ProServe team, we've got all of the back end that you can build solutions on. So really, you're just setting up a subscription to our data. You can prototype in a low-risk way, put all that data through the cloud, build your pipeline out, and bring it into your application. We've got lots of partners that have built really cool solutions on top of this for agriculture. You'd recognize, hopefully, some of the names in here. A number of them have worked with us for many years and have come up with some really unique solutions. I'll mention a few of them here just before I close. Some of these will be use cases you're familiar with, so the kind of standard one that we use imagery for, crop health monitoring. Change detection is something that people have been talking about for many years to be able to do from satellite. It's not really been that successful given the limitations of image quality and revisit rates. So we're there now in detecting change, and then maybe you're ground scouting, or maybe you're sending a drone to go see what that change is. We've got some people that have done some really impressive modeling, backtracking to figure out exact sowing dates based on our imagery time series, and harvest timing and validating the activities that are taking place over the landscape. We've got a number of researchers now looking into soil sciences and soil health with our imagery, correlating all of the nuanced changes in the vegetation above ground and some of the surface properties of the soils for soil health and carbon. This is one that has been a challenge to do from remote sensing, but we're doing it better than we ever have before. Crop classification and yield forecasting. Take an entire province, for example, pick out where the canola is, figure out the yield forecasting weeks in advance, and then kind of converge that model. Precision irrigation management, we've seen this done with very large area pivots. We're not at the level of detail that you would see with some of those on-pivot sensors, but it's definitely a good starting point to understand your management practices and optimizing those. Field boundary delineation, you can't do a lot of precision ag work without field boundaries. So for those of you that are after that, that's something that we've got some partners that have built some really cool solutions on. And then this is relatively new. We've seen people using our imagery to optimize grazing when they're moving cattle from place to place, or whatever livestock you have grazing, for rotation optimization and making sure that they're not overgrazing, undergrazing, and really improving efficiency. So we've got a partner that's been building a pretty amazing solution on that as well. So they work with us for these reasons, right? We've got reliable data. It's always coming. We're not as susceptible to failures of sensors out in the harsh conditions of space. The precision that you need, so repeatable information over time. Scalability, if you're trying to scale out with something like a drone or an airborne program, it can be difficult. And then efficiency in actually accessing that data. So there's a fairly short list of use cases. I'd love to dive into each one of those in more detail, but there's so many more things that people are starting to do with our data. And really, I want to turn it over to everybody here if there's interest in talking more about what you would do with that. We want to see people explore that and make that information as accessible as possible. So thanks for your time. I think we might have a little bit of time for questions.
Yeah. Thank you, Cassidy. Very nice talk. And so my question is a bit different. Like when I see the Planet satellites as compared to other Sentinel-1 and all those single satellite, like Planet have hundreds of small pieces of satellite going on the space. So my question is about, like, we always talk about the pollution thing is on the land, and like air and atmosphere doesn't belong to anyone. We can pollute them. And now there is a talk of like debris or all those small things going on the space. And bringing back is not easy task. So as a Planet, you have any comment like what is the future? Like there is a lot of advantage of having precision agriculture and things are going very well. But in terms of like numbers, when I see in the Planet like launching like new satellites with a lot of new improvements, how you see after like couple of like decades about those debris play a role in space pollution?
That's a great question. Is this guy on? Yeah, here we go. So the nice thing about our satellites being so small, that when they run their lifespan, we can deorbit them, and they'll burn up entirely on reentry. So there's little to no risk of them making it all the way down to the ground and causing accidents. That's not the case for a lot of the stuff that's up in orbit. So that's one benefit, but really the challenge of how crowded things are getting in low Earth orbit and mid-Earth orbit, you could find a lot of really cool websites you can go to and actually see what those look like in real time. It's pretty crazy. So Planet is actively trying to be part of the solution there. There's always this kind of underlying risk that there's going to be some catastrophic like collision event that cascades through all of these networks and breaks things. And that can happen if we don't vigilantly monitor it. There's a lot more space up there than it seems when you look at those visualization tools. There is a lot more room for these things to kind of move around, but we don't have the same risk for things falling down and causing accidents. We don't contribute to nighttime light pollution, night sky pollution. That's a real challenge. I don't know if any of you have seen like Starlink's stuff going across the sky. It's pretty scary when you actually see it getting launched and all of them are bright and together. Ours are solar Passover, solar noon, so we don't actually see them at night, which is nice. So we're trying to actively make sure we're not polluting the night sky. And as we get more and more players in what we call new space, the new space industry, we actually have to build like regulations around this stuff. So we have space lawyers at Planet. That's actually what they're called. And there is a space court that's being developed with regulations around this stuff, like who's accountable if one satellite hits another satellite? How do we keep those people, liable for those things? All of that's being built right now. It's still a little bit of the Wild West. And so we're trying to actively kind of promote responsible use of that space.
That's great. It's good to know that you're focusing on that too as we're working on a better world. Are there any other questions for Cassidy? All right. Well, then thank you very much, Cassidy.